First of all, thank you so much for staying out late. I know it's the last talk and you guys are probably tired. Um, Thank you. My name is Kamoltat. Some of you might know me by Junior. And today I'm going to be talking about supporting 3 availability zones in the stretch cluster. So our agenda for today, I'm just going to introduce what I do and the challenges with traditional stretch cluster setups, how stretch mode, which is 2 availability zones, can solve these challenges, and how we can expand that to 3 availability zones. And I'm going to talk about some current limitations, some of the short-term solutions I have for that, and some of the long-term solutions. So a little bit about me. I'm an engineer at Ceph. I'm in the Rados team. I've been contributing Ceph for 4+ years now. Some of my key contributions is stretch cluster, stretch mode, the autoscaler, and I've worked on some of the tautology stuff. All right, so what is a stretch cluster? A stretch cluster is basically a cluster that spans across multiple geographical locations. So it sits behind a wide area network. It's different from your traditional behind a local area network in like one data center. So in this example, the cluster spans across 2 data centers. And with the connection being high speed and low latency, it should be able to withstand net split, conserve I/O if one of the data center goes down. On the right-hand side, I've included the stretch rule, which is the crush rule for a 2-site stretch cluster. So basically what the rule says is that when you write the data, you pick 2 data center. And you basically write 2 copies of the data to each data center. So the replication size here is 4. And the minimum size of replication for a PG to be active is 2. Here, I've included quorum. So here, monitor A, B, C, D, E, F, all the monitors between both data centers are in quorum. And I've included an example, PG 1.1, has the acting set of OSD 0, 1, 3, and 4. So those are the 4 copies in those 2 data centers. So as I'll be explaining and demonstrating, these variables would stay there and change, so it's easier for the audience to follow. So I'm going to talk about how we monitors are elected. So a leader monitor will be elected using connectivity strategy. What this is that each monitor will maintain a connection score of its peer, and the scores are shared between all the monitors. And the monitor with the highest score is elected the leader. And if the scores are tied, the monitor with the lowest rank wins. So leader monitor is in charge of all the decision makings in terms of like requests, all the requests that its peer monitors, it will get rerouted to the leader monitor, and it has basically the authority. I'll give you an example what the connection scores will look like. Here, monitor A has its own score. It has its own opinion about Mon B and Mon C, its peers. And also, it holds the peer report. So it holds what Mon B thinks about Mon A and Mon C. It holds what Mon C thinks about Mon A and Mon B. So in election, when you're trying to figure out who is best fit for a leader, what you do is you sum up the score. For example, here, Mon A is competing against Mon B to see who becomes the leader. You sum all the opinions about Mon A, and divide it by the number of peers that it has. So it has a 0.96 score, while Mon B has a 0.56 score. So the monitor A wins in this case. And with stretch cluster, with the setup you previously seen, there are 2 things I want you guys to remember as a problem. One is net split, and one is peering rule. I'll be talking about net split first, and how with this traditional setup, why it won't work. So imagine there's a net split between DC1 and DC2. So the monitors will try to send a proposal to be a leader. and the voting will get started. So obviously, every monitor will try to become a leader, but for the sake of simplicity, on the left-hand side, I'm just going to include Mon A versus Mon D. And obviously, Mon A will only have its peer monitors in DC1 that votes for, because it can't talk to the monitors in DC2. So it only gets the votes from DC1. And Mon D is the same thing, but it's in DC2. So it can only get the votes from its peer monitors in DC2. So here, no one wins, because you need the number of votes to be more than half of the quorum size. So on the right-hand side, we see that the quorum size is 6. And so 3 is not more than half. So the problem is that the election will cycle forever. So that's one thing about net split problem, where monitors might get stuck forever if the setup is like this. Next is peering rule. So what is peering rule? So it's a set of conditions to determine whether the OSDs in the acting set can safely peer with each other. And it's also crucial in determining if a PG can go active or not. So here, obviously, the rules are more complicated, but I wore it down to very trivial, where normally it would be if acting set size is more than or equal to the min size, the PG can go active. And I want to demonstrate in the next slide why, with this trivial rule, we might run into some problems. So the first problem we might run into, I want to demonstrate, let's say PG 1.1 has version 10 across the board, and suddenly OSD 3 and 4 in DC2 goes down. All right? So the acting set for 1.1 is now 2, right? So that size is now 2, which is equal to the min size of the cluster, which means that it can still serve I/O, can still go active. So let's say DC1 gets some writes, and the version becomes version 11. But then something like a catastrophic event happens where, I don't know, DC1 catches a fire. So now what happens? Now we don't have the latest copy anymore, even if OSD 3 and 4 gets restored. So what we have here is data loss. And so how do we solve this problem? So a great colleague of mine, Greg Farnham, he's the original author of stretch mode, and it is the solution to both of the problems I presented to you. Stretch mode setup is a little different. The only thing being different is in this setup is it has a tiebreaker monitor in a third DC, and that third DC only has that monitor. And its sole purpose is, as the name says, is to tie break in an election. So let's simulate what we did from the last slide, where election got stuck forever. So let's say Mon A proposed to Mon G, and Mon D at the same time, Mon D proposes to Mon G as well. Here we have net split between DC1 and DC2. And so Mon G has a decision to make, right? And so let's say Mon A's proposal gets to Mon G first. And Mon G's protocol will be, OK, I will lock you first, since you're the first one. And so Mon A now has more votes than Mon D, but it also has more votes than half of the quorum, which means it wins the election. So we can elect a leader, and the cluster is now functional. So what happens to DC2 then? So quorum is changed. On the right-hand side, you would see that quorum is now monitor A, B, C, and G. So basically, in stretch mode, you keep the DC, you pick one side of the cluster to survive, and you kind of like kept the other side of the cluster who loses the election in the dark. So DC2 is in the dark, and we can continue to operate with DC1 and DC3, but there's a catch to it. It's in a degraded mode, meaning that the size gets reduced by half. So before the replication size is 4, it becomes 2. Before the min size is 2, it becomes 1. And so when there's I/O, it only stores 2 copies inside its own data center, and not trying to store a copy on this DC2, which is kept in the dark. PG 1.1 acting set has a size of 2. I know that the peering rule states that it needs, we'll get to that. Sorry, I was jumping the gun. Okay, so what I was about to talk about is stretch mode has a stretch peering rule, which states that, other than the acting set size being more than or equal to the min size, and it allows the PG to go active, acting sets must contain OSD from multiple data center to serve I/O. So what this means is that the acting set cannot contain only OSDs from, let's say, in DC2. It has to contain some OSDs in DC1, at least one, in DC1 as well, before it can go active. So what will this change? Let's run through the scenario I showed you before where we had data loss. So let's say OSD 3 and 4 goes down, and the acting set size becomes 0 and 2. Usually with the old peering rule, you allows it to go active, right? But not with this new one, where it states that you need some OSDs from DC1 in order to go active. So it prevents PG 1.1 to go active, meaning if fire catches in DC1, we still have version 10. So noted data loss there. Even if OSD 3 and 4 gets restored, data is not lost. So stretch mode in degraded mode, it triggers when all monitors in this data center fails. So if all monitors in one data center fails, basically the OSDs can't really connect to it, and clients can't connect to the monitor. And so we also decrease the min size, as I mentioned before, to 1 and size to 2. But the most important thing is that in degraded mode, this is a special case. So you have stretch mode, and the subset is degraded mode. The peering rule gets changed again, allowing the surviving site to serve I/O while having only OSDs from one data center. So before I was saying that you need at least 2 data center in the acting set, but degraded mode is a special case for stretch mode. So stretch mode only works with 2 sites, and stretch mode is a cluster-wide configuration. How do we expand it to 3 sites? Well, we basically have to have some tunings with the stretch peering rule, because that's the most important thing. So in order to deal with that, I exposed some of the variables of the peering rule, namely peering crush bucket count, peering crush bucket target, peering crush bucket barrier. So you can use this command, Ceph OSD pool stretch set, and you can set the certain values to enable you to utilize the peering rule for 3 sites or 4 sites. I haven't tested with 4 sites, but the opportunity is limitless. So what is, I'll go one by one what each variable means, such that when you go back home, you want to try running a 3-site stretch cluster, you have a better idea of where the numbers come from. So peering crush bucket count is basically the minimum number of distinct crush buckets, or in this case, for our example, is data centers. An acting set is expected to have in order for the PG to peer successfully. So for 2 sites, this value would be 2, because we're expecting it to have at least 2 distinct data center in the acting set. With the only exception being in degraded mode, you change this value to 1, okay? And let's see how this plays out in a 3AZ stretch cluster. So here we have, let's talk about the rules first. The rules are slightly changed, where you basically choose 3 data center, and you basically write 2 copies into each data center. So the size of this cluster is 6. The pool is 6. The min size will be 3. And quorum, we'll have A, B, C, D, E, F, G, I, and PG 1.1 will have a size of 6. And so let's run through the same scenario that we did. So let's say DC1 and DC3 goes down. While we set the peering crush bucket count to 2, meaning we need at least 2 distinct data centers in the acting set for us to go active. In this case, the acting set might choose OSD 5 to be the candidate, with the acting set being the size of 3, it meets the requirement of min size 3, right? It should go active, but the peering crush bucket count being 2 states that, well, you only have 1 ancestor, meaning you only have 1 data center in this acting set. You can't go active. So by tuning it, this peering crush bucket count, you can successfully avoid situations where you have data loss. The next thing I want to talk about is peering crush bucket target. So it is used in conjunction with the size of the pool to determine the maximum number of OSDs that it can, from the same data center, is allowed to choose to be into the acting set. So it's used to calculate bucket max, and why bucket max is so important. So bucket max basically prevents you from, if you lose a data center, prevents you from shoving like 3 data centers worth of replica into a single site. So it limits the number of OSDs from a particular data center to be in the acting set. And how do we get this bucket max? So I know this calculation is a little convoluted, but I promise you it will help you to see clearly why which number you should pick for your peering crush bucket target. So essentially you divide the size by peering crush bucket target to get the bucket max. And as you can see, the number of sites as it increases, it correlates to the peering crush bucket target. So for, let's say, 3 sites, you have 6 acting set size of 6, right? And you're saying you have 3 sites. Well, you only want 2 OSDs from each site because you want it to be balanced. If, let's say, if the bucket max is 3 for 3 sites, then data center 1 might have, you might store 3 replicas in there. Data center 2, you store 2. Data center 1, you store 1. So it's not balanced. So 2 for a bucket max is a good balance, and I will demonstrate why this might come into play when faced with certain scenarios. So here, bucket max is 2, meaning when there's failure in DC1 and DC3, instead of PG 1.1 picking OSD 5 as the 3rd OSD in its acting set, it will say no to it because it already has OSD 3 and 4 from DC2. So yeah, again, the peering crush bucket target creates this bucket max, which basically prevents us from overloading DC2 and potentially also going active and facing a scenario where there's data loss. So I want to talk about some limitations with 3 availability zones. So currently, right now, we have a split brain problem if we were to do a net split between 2 data centers. So I will demonstrate to you what I mean by that. So again, we have our 3 availability zones, and DC1 and DC2's connection is cut, so there's net split between them. So OSD3 from DC2 starts reporting that, oh, I think OSD0 is down because I can't reach them, and I don't have heartbeat. OSD4 also reports that OSD0 is down because did not hear back from them. So the leader monitor marks it OSD0 as down, but shortly after, because we have connection with DC1 and DC3, OSD6 in DC3 reports that OSD0 is up. I can talk to this guy. And OSD7 reports that OSD0 is also up. So the leader monitor then marks the OSD back up again. And this cycle continues endlessly. And the PG gets stuck in peering because of this. And no I/O gets received. So we're in a little pickle. So one of the shorter term solution, more like a remedy, not a solution, like it helps. I wrote a function where you can detect net split in a monitor. Basically, if a monitor can connect to like everyone, and then it sees that, well, there's a pair of monitors that are disconnected, yeah, I'm sure there's a net split between them. So basically, a net split warning would get reported in Ceph status. And but a longer-term solution, obviously, if you guys have already figured it out, is we need to pick one side such that we can operate with just two sides, right? We need to basically say, okay, well, we gotta choose which OSD, well, we're gonna mark down, and just forget about it. And yeah, I can utilize the stuff that I wrote for the monitors to be able to detect net split to basically confirm that there's still net split happening. So, whoever gets reported, the OSDs that get reported down first, well, they can be in the dark. And the monitor, once net split is resolved, the monitor will get notified, and it can bring it back up, and just everything remains normal. This is just a theory. Haven't implemented this yet, but yeah, that's basically the long-term solution for that limitation. So currently, 3AC is available in Squid and in main branch. So please do play around with it. And yeah, I think that's it. Thank you very much. Any questions? Yes?
Yeah, we have 3 data centers now, migrating to being in 2 data centers mainly, production load, and we have one that is pretty much offload. Should we then go with the split model with one tiebreaker? Or?
Yeah, if you want to have, to replication of, so like let's say if you want a replication size of 4, then yes, you can opt in with it. But with 3AC, you can have a replication size of 6, although the trade-off is that you might have to put more resources in that third data center, right? And obviously, net split could be an issue. So yeah, I would recommend starting with stretch mode with 2 sites first. And then once 3AC is more stable, I think it would be interesting to see if you can have higher availability in your cluster. Sounds good? Yep. Okay. Yep.
Will it work also with erasure coding instead?
Good question. I think that question has been around for a while. Currently, no, it does not, sorry. We have plans to support that. I think with erasure coding, you gotta be a bit careful. With the parity chunks, it's like 4+2 or something, 2 parity chunks. You can't locate them into the same data center, right? So if it fails, then it's gonna be bad. You can't recover it. And also, when you're trying to, reassembling the chunks, it takes quite a lot of load, and also you need a pretty good network. So that's something that, I've been thinking about. There's a lot of moving parts and things that I need to be aware of for erasure coding. But yes, eventually I think we would want to support that. Yes, Travis.
Yeah, what's the advantage of using a 3 availability zone solution for stretch instead of just a normal 3 AC cluster, like with just 3 replicas and 3 mons? Why would I use a stretch cluster with 3 ACs?
Yeah, well, with 3AC, you can basically use some of the peering rule, the new peering rule that I suggested, such that you prevent some scenarios where you can have data losses. So I think that's an advantage. Yeah. All right, seems like no more question. Thank you guys very much for staying until the end. Yeah, I really appreciate it. Thank you.